Hi everyone, my name is Mario and this is the presentation of the LSI UNED team for the CLEF eHealth 2020-1. As mentioned in the overview, this task consists of the annotation of ICD-10 codes on Spanish electronic health records. For this purpose, 1000 real clinical cases have been provided, which includes misspellings, acronyms, unstructured phrases, and a wide variety of specialist terms. All this diversity makes the task complex as it involves a huge number of different patterns. In this context, supervised systems are facing extreme distributions, in which a few codes appear frequently while the rest are rarely associated with the records. Thus, frequency tends to follow a power law function, which implies limitation for supervised learning. This is the case of the provided clinical records, as you can see in the training code histogram shown in this slide. The number of instances has been represented in the y-axis, while the codes are represented in the x-axis. As you can see, there is a majority of codes with very few instances, not enough to generalize patterns able to predict future examples. Furthermore, the European General Data Protection Regulation, or GDPR, strongly limits the availability of data. Both factors make it necessary to explore alternative techniques to machine learning methods. Considering this background, we have proposed an unsupervised approach based on conceptual similarity. This is the gray flow above in the pipeline. And this is complemented by machine learning algorithms. This is the yellow flow below. As for the gray flow, the main idea is to identify SNOMED concepts in ICD description and clinical records. In this way, we have groups of concepts characterized in both the different codes and electronic health records. We have included bag of words to that representation in order to try to avoid the loss of information caused by vocabulary not included in the ontology. We have used the provided annotation and the description of all final codes. This means more than 20,000 different diagnoses and more than 70,000 different procedures. Here is an example. On the left, we have the Crohn's disease of a small intestine with intestinal obstruction code, which is represented by two different SNOMED concepts. And on the right, we have one piece of an electronic health records, which is represented by another two different concepts and three different words. The next step, the second one, would be to estimate similarities among the new representation, those composed of a set of concepts and words. So first, we have computed the similarity values between individual concepts from electronic health records and code descriptions. To this end, lean measure has been used by comparing specificity and common parents. In turn, we have used lexical matching for words. It will be interesting to use word embeddings for getting a semantic instead of a lexical similarity, but we haven't applied them to reduce computing. As mentioned, we have used more than 100,000 different descriptions. In the example here, we have 4 different possible pairs for concepts, and I don't care about the words because we don't have any word on the left representation, so those similarities are going to be 0. Then, once individual similarities have been computed, a pairwise assignment maximization problem is applied to get a score value per ICD code. The idea is to find which elements from ICD description could be more similar to those from electronic health records. So, by associating pairs of elements, we can determine a similarity value between sets. Then the final score is calculated by averaging all pair similarities, and then this is used to rank the codes. As for the unsupervised part, binary classifiers are used to predict the presence or absence of codes in the records to address a multi-level classification problem. So for that, gradient boosting has been implemented as it works well in such unbalanced scenarios. Those algorithms focus on the iterative reduction of the error during learning. Then the confidence of codes are used to run the result. We have used the annotated PubMed abstract provided by the organizer in addition to both the development and training dataset. Finally, both ranks are joined, prioritizing machine learning. This is because only patterns for the most frequent labels are learned in such extreme scenarios. So supervised algorithms are expected to produce results with higher precision, but lower recall. This is because machine learning algorithms are expected to learn complex patterns, but in such a scenario they are going to ignore many labels. So we have reached the following result with the 5th, 7th and 6th position in the diagnosis procedures and explainability subtasks respectively. The last one, the explainability subtask, requires evidence, so only the unsupervised part has been used there. Here are the same results but disaggregated by position in the rank. In this case, F measure is shown for the first, second, third and so on until the 25th position. As one can see, F measure is worse for the procedure subtask. This is the yellow line. This is because procedures have longer description involving a larger number of entities. So it is more complex to establish the unique similarity value between a larger number of elements. Also, it decreased rapidly because the number of procedures per document is lower and more diverse. Besides, competitive results are achieved in the explainability subtask, despite the introduction of errors due to procedures and the lacking of the contribution of machine learning. Well, but how does the system perform when faced with new instances? On the left, we have represented the distribution of codes for the training and test dataset, showing the ranges from 1 to 5, from 6 to 15, and over 16, including unseen codes. In turn, on the right, we have shown a F measure for the same frequency ranges. Results up to 0.26 and 0.5 are achieved for zero-shot and few-shot labels, respectively. Codes with greater representativity, those with the frequency highest, achieve higher F measure values because machine learning algorithms are applied for the two first subtasks, and because maybe a greater number of annotation improve the name entity recognition process. Well, that was our proposal, so if you have any question, please feel free to send me an email to the first address in this slide. So thank you for your attention and bye.